Today we're going to start talking about bootstrapping. That's what we're going to start exploring today. We're going to talk about the general issues, the general concepts, and then we'll start getting into IA32 specifically, because obviously that's what you're going to have to work with. But basically we have this issue that we have a machine that requires a program. But when we turn it on, it doesn't have a program. So the question is, how do we actually get to the point of running our program? That's what bootstrapping is really all about. And so there's this thing called the bootstrap process. It's I think I actually say it on the next point, that it derives from this phrase, pulling oneself up from one's bootstraps, which I don't think that you can draw like the physics, like force diagram that shows how that works. But the concept is I have a self-sustaining process of progression where I load each the subsequent step, and then I can start executing, and each step is part of the bootstrap process. So the thing that I think you'll find most interesting is that it is a series of bootloaders, or a series of bootstrapping programs. It's not just one, and it's not just two. There's actually typically quite a number of them involved, and each stage has a simple job. Cross the bridge to the next stage, get the next stage going, and then each stage gets progressively more sophisticated. So currently we use read-only memory of some kind. Now when I say read-only memory, of course that is a loose definition of read-only memory because typically it's electrically erasable, and so maybe it's not even a very accurate term anymore. But something has to be somewhere for the processor to start executing code. So that tends to be how we do it. But you might have wondered, how did they do it before read-only memory existed? And it turned out that there was a variety of unusual ways that people would get these computers started and start executing some programs. So you have to read some limited number of instructions somewhere and then begin executing them. So we used to have punch card readers, and I'm a little bit sad. I still have this dream, since I never got to program a punch card computer, that maybe I'll actually build a punch card drive and hook it up to a computer and actually use it. It'd be really cool to have, I keep thinking of all these old devices, it would be cool to have a USB port on. Like, yeah, here's my USB drive, and it's a shoebox full of punch cards, and if I need to read it, then I just start scanning through punch cards. But anyway, if you had a punch card reader as part of your computer, then what you would do is the bootstrap process would read the first punch card into some memory location, and then just begin executing the instructions on that punch card. So your first punch card was always the bootstrap punch card. Okay? And then that would tell the computer how to get the rest of the computer going. Sometimes you had a bank of switches. This was really common to have a bank of switches to either say, this is the first instruction you should execute, probably more for a CISC type architecture where you could have it do a lot of things, or here is the first N instructions that the computer should execute. So IBM 650, just to give you a few examples, 1953 had a bank of 10 10-digit switches. So it had 100 switches that you could set that would basically be the first instructions to start the computer running. And typically they would say, go get me a punch card's worth of data or a couple punch cards worth of data, load them into a specific address, and then start running that information. CDC 6600 had 12 by 12 toggle switches, so it was a little bit more sophisticated. It was called the dead start panel because it would start the computer from when it was just previously dead. And that would be the first 12 instructions for the computer to run. And then presumably that's enough to get it going to the next step. But you can see how limited this is in what you have space to accomplish. And so clearly it's a multi-step process because this is going to start the next level, which is going to start the next level, and maybe there's even more levels after that. The Altair was one of the ones that you may have heard of this from sort of the distant, hazy computer past, where you actually had a bank of switches and you would set up an instruction and then you would push a button and that would load that instruction, and then you'd set the switches and load another instruction, set the switches, load another instruction, and so forth, until you'd entered all of the instructions for the bootloader, and then you could tell it to start and would begin executing those instructions. Now thankfully this didn't have to be done too often because I believe this was stored into magnetic core memory, and magnetic core memory holds its contents when it's turned off. So frequently you would not have to do this all the time, you just had to do it every once in a while if something horrible happened to your computer. An electromagnetic pulse or something like that. You also had diode matrices, so if you don't have transistors in some read-only memory, then you could always use diode matrices. And so you can see that these would allow you to specify more sophisticated bootloaders. So you have a diode, then you have a 1, and in absence of a diode would be a 0. You can basically get onto eBay and look for memories of all these various technologies. There's people selling them to people who have various, they're just missed the past. And there's a couple of other really unusual memory technologies, which I don't talk about in this class, but you come across them and you're like, wow, people store data that way? And it's just really kind of a weird thing. Okay, so obviously once we have read-only memory, then that makes things much, much easier. You can cram a lot more information. So now you can actually have our boot loading subsystem provide real facilities. So like I say here, we have sophisticated programs, basic drivers for disks, video, minimal operating systems, if you can call it that. And when we get to UEFI, you'll be like, wow, okay, that really is a basic operating system that is responsible for loading other operating systems. It's pretty sophisticated. And of course, this read-only memory, or memory that sticks around when the power is off, so we call it persistent memory, and the program you store in it, that's called firmware. And of course, initially it could not be rewritten. If I wanted to upgrade the BIOS on my original computer, which was an AT, it's all we had, I'd have to get in there with the screwdriver, pop the chip out of its socket, and get another chip and plug it in, because that was basically what we had to do. Now it's pretty easy. You typically boot it into some program that can access the hardware directly, and it can just reflash the BIOS relatively easily. Okay, so this is where we're at now. And with UEFI, you just dump more programs on the hard disk. It uses the hard disk for storing boot software. Now, I just wanted to mention this. It actually doesn't fit very well into the lecture flow, but I just think this is really funny because Apple actually was capitalizing on how difficult these computers were to use, even back in 1976. So they had this ad that they ran in a magazine. You don't need an expensive teletype. Using the built-in video terminal and keyboard interface, you avoid all the expense, noise, and maintenance associated with a teletype. So you don't need that printer on the output end to print out the results of your program running. And the Apple Video Terminal is 6 times faster than a teletype, which means more throughput and less waiting. So they were excited about that. Then they had this section. No more switches, no more lights. Compared to switches and LEDs, a video terminal can display vast amounts of information simultaneously. The Apple Video Terminal can display the contents of 192 memory locations at once on the screen. That's a lot. Well, at least it was back there. And the firmware in PROMs enables you to enter, display, and debug programs all in hex. What a win. From the keyboard, rendering a front panel unnecessary. The firmware also allows your programs to print characters on the display, and since you'll be looking at letters and numbers instead of just LEDs, the doors open to all kinds of alphanumeric software. Wow, wave of the future. So this is where they were at. I mean, it was like a huge deal. And of course, they sold it for an unusual price. Which they thought initially was just funny, and then they didn't, they later discovered the furor that they unleashed by proposing this price. Obviously pissed off a bunch of people. But it was kind of a big deal that they were putting this kind of thing together, and it was a big step forward. Okay, so what we're going to do next, there was something else I wanted to say about IA32, oh yeah, that's right. If you happen to have one of these old Apple computers, Apple ones, you can sell them for like a couple $100,000 now. It's crazy. They're real collector's items. So some of these things, you could probably build an Apple I for a 5X project. Like, it's that simple. And a lot of these early microcomputers, you could build as a 5X project. You could probably even put them all on a programmable device. I mean, it's crazy how much things have shrunk. But, if you happen to have the original device kicking around, you can sell it for quite a lot of money now. So what we're going to do now is cover IA32 Bootstrap because basically this is the platform that we're going to be working on all term. And it's the platform, you probably have one in front of you, many of you do. So it's just really common, and it's not too dissimilar from other processors. So it definitely gives you a sense of the difficulty, the challenges that arise. Also, especially on a processor that has a long history. Okay, so operating systems run on hardware. Hardware is complicated, and this is really true of IA32 because sort of the personal computer platform, the Intel processor-based personal computer platform, has been around for a long time. Early 80s, and a lot of the hardware, they've actually retained backward compatibility all the way along. In fact, when you work on your second assignment, a lot of the documentation is for devices that were physical chips on the motherboard back in the PCXT days, and they're pretty straightforward to program. We don't actually work with the more advanced hardware because it's just too complicated. So we just work with the old versions that are still supported even on modern computers, which is kind of fun. So well-designed operating systems do obscure these details, thankfully. And you can't avoid them, though, in the Bootstrap process. And you'll see this when you want to configure some device and you have to send data to its ports to get the device to do various things. And so you'll see some of that in your PC booter. But a lot of that is even obscured by the facilities I give you. IA32 processors, when they start up, they automatically start executing instructions at a specific address. So that's the address that they specifically start executing at, and you could ask the question, well, what happens if you don't have enough memory? Well, then you just throw away address lines and you ignore them, and you just use the lower address bits. So you just make sure that you put a memory where those addresses, or where that address sits. And so then you can say, these are the instructions to execute. Now you'll see that you start at F0. So how many instructions do you have? Well, you have 16 bytes, basically 0 to, F0 up to FF. That's all the bytes that you have. So what do? You put a jump there to something else that's much more interesting. So you'll plop a ROM in there, and that first instruction will be go to the actual firmware that I want you to use for booting. Also, the processor starts off in ring 0 because I should be able to do anything that I want at this point. And so that's really nice. You'll also notice that for the PC booter that you can do anything. You can talk to any of the hardware that you want because you start out in kernel mode. And there's two categories of bootloaders. You may already be familiar with this, but there's PC BIOS, which we'll talk about this time, and then EFI, which later became UEFI when it became standardized and actually became more widely utilized. There's still not great support for UEFI across the board. Apple tends to bend the rules on it, so you can't just necessarily boot anything on a Mac unless you really try to jump through some hoops. But generally, it's getting more and more widely supported. So PC BIOS, this was the first firmware that was on x86 computers. And basically, it's the same issue that we have with operating systems. Okay? We have certain facilities that programs need, except at this point, our programs are bootloaders, trying to get the system up and running. So the first feature that we have is a firmware bootloader to start the Bootstrap process, a library of basic operations we might want to perform with the hardware, so that I don't have to think about all the details. I don't have to say, hey, what kind of hard disk are you? What kind of floppy disk are you? Thankfully, we don't have to ask that question anymore. How do I change into this graphics mode? I have no idea what graphics hardware is in place. All of that is encapsulated in the BIOS, and it's exposed through a few simple operations. And then the nice-to-have feature is a user interface for configuring your computer. Probably many of you have used this kind of user interface. You go in, you say, here are the hard disks that I have in my computer, here's the current system time until you get NTP running or something like that, and you can synchronize against a time server. All of those kinds of basic issues you can go in and configure in your BIOS. Okay? This approach started back in, you can see, the 70s, which is kind of shocking, just after I was born. That CP/M was an operating system, and it needed the ability to interact with the computer hardware. You kind of had two approaches. Apple was really constraining on what hardware it would support. You support, we're going to run computers with our hardware. You can't just plug any random stuff into it. You can only use our hardware. Personal computers were very different. You could plug anything you wanted into them. And so that obviously made it difficult to support from software, and so the BIOS really helped to sort of cover over that variability you could have in the hardware. And so, like I say here, the BIOS was originally loaded from disk by firmware. And, of course, you started out with IBM. IBM was the first company producing personal computers. and they were kind of expensive. I remember because I wanted one, and we didn't get an IBM initially. We went and got a clone. And what people would do is they would study the IBM personal computer system, and they document it, and they do this, they call it a clean room implementation. One team would sit down, document everything that they could about how the personal computer worked, and then they would hand that manual over to another team that never studied it, and then that team would go about implementing a system following the documentation that was reverse engineered. And so that's how the first clones were created. They didn't always do a perfect job, but they did a pretty good job. And clearly, if they're going to support the same software that the PC supports, then they have to have the same BIOS operations supported as well. So it became a de facto standard. It wasn't agreed upon across the industry. It just sort of arose on its own. And the BIOS bootloader is very simple. So remember, we already had the processor resets. It starts at a particular address. It executes a few instructions, which jumps to the BIOS. The BIOS does, querying of hardware, set up its interface for programs to be able to utilize, and then it starts doing its own boot process. So we have 2 steps now already, and now we're getting ready to do the third. So if a hardware reset was performed, check the hardware. So you have that power on self-test, maybe hear the beep, or you'll have, if there's an issue, beep, 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 and it'll make various sounds to indicate what problem has occurred. Hopefully you've never encountered that. When it does, you kind of are sad and you get on the internet and look at what the beeps meant so that you can try to figure out what's wrong. But you have a few things that are performed when the computer starts up from a cold reset or a hard reset. And so yeah, like I said, it looks at the computer peripherals, figures out what is available, and then what it does is it goes through the bootable devices or all the storage devices that are on the computer that it knows how to talk to, and it looks for a bootloader to start the next stage. And it brings it into memory and then starts running it. Now, it used to be that it would always just go through the floppy disks. That was always the way it would do it. Go through all the floppy disks and then go through all the hard disks. That's how the BIOS originally worked. But now, of course, you can configure the boot order or even exclude things. Like, no, I do not want to boot off the network. I don't want my computer, hacked right off the bat or something like that. Or, make sure that you turn off USB booting so that you don't accidentally cause yourself some trouble. Okay. But the first sector was brought into memory. It was only 512 bytes. We'll talk about some of those constraints in a moment. But each drive's first sector would be brought into memory. And if the last 2 bytes of that boot sector were 55 and then AA, then the BIOS said, this is a boot sector, and it would start executing it. If it didn't have 55AA, it's like, well, this isn't a bootable disk. That's how it would tell. Okay? Any questions so far? And if one of your questions is, did it really work this way? Yes, it still does, actually. This is still basically what it does. Okay, so the BIOS has successfully identified a device with data on it. It has successfully loaded the first sector. It has successfully identified the boot signature 55AA. So it loads it into this address 7C00, and then it jumps to the beginning of it. And that's basically all the BIOS does. It's like, okay, now it's somebody else's job. So now we're on stage 3. This boot sector is only 512 bytes. That's not a lot of space to do stuff. Okay? The reason why it's 512 bytes is that this has been the size of sectors forever, except now that it's not, we're actually starting to move to 4 kilobyte sectors, but those drives are still capable of emulating a 512 byte sector for this kind of purpose. But I have a feeling with UEFI, we're going to start stepping away from that more and more. So UEFI is kind of the wave of the future. And BIOS will become less and less common. It'll probably also change the way that we teach this Bootstrap process mechanism. The kind of assignments you can do will change a lot. But anyway, you can see here we have 200 hex bytes or 512 bytes. So the bootloader occupies these addresses, 7C00 to 7DFF. Okay? We have 510 bytes to do our thing. The BIOS doesn't leave the bootloader completely in the dark. It actually tells the bootloader what disk drive it came from. So in DL, it actually passes a number that says this is the drive number of the drive that the bootloader was loaded from. So if the bootloader just wants to pull more data off the exact same disk, it can just use DL for the drive number and pass that to BIOS functions, and it can suck the rest of the program off of the disk. That becomes really helpful for our PC booter, because DL will have the PC booter's boot sector drive number, and we can just use that same drive number to load the rest of our program into memory. Okay. Bootloaders, almost always written in assembly language. It is exceedingly rare to see a bootloader written in another language, and if it is, it's typically a really bad idea. Because the programming is not hard, and the space is at such a premium that you want to be able to make sure that you're going to be able to fit everything into the bootloader. Now, just again about the assignment, I'm really glad that you guys are doing a PC booter, because it means that you have a lot of space in that boot sector to do your thing. When I finished my solution version of the bootloader, I still had basically half of the boot sector left to put whatever I wanted into it. That's a lot of free space if you're writing a bootloader. The previous lab that we did for bootloading, students were frequently overrunning the size of the boot sector, which is really annoying. It forces you to think very carefully about how you program stuff in the boot sector. Thankfully, we have tons of space, so you don't have to be really cautious about that. You can be kind of relaxed and not worry about those things. You can follow good software engineering practices and not write spaghetti code, because you don't have to. So this is why it became hard the last time we had a different lab. You have disk partitioning, which was a mechanism that allows you to store multiple logical drives or partitions on a single physical device. So that first sector doubles as a master boot record. Okay, so it has a bootloader in it, but it also specifies details about those disk partitions. And so like I say here, it's up to 4 partitions, each with its own format and use. Each partition would have a type that says this is the kind of operating system, or this is the kind of partition. And then operating systems would be able to identify their own partitions when they boot by looking at the partition types. And you may even have OSs that require multiple partitions. I mentioned a couple I only mentioned Linux here. Historically, it was really common to create a swap partition for Linux. Now Linux can also use a partition file, so you don't actually need to have a separate partition anymore. What else? Windows was really interesting in that its bootloader could only load its information from a certain point. So you frequently had a Windows boot partition that had to be a certain size, and then you could create another partition for the rest of the operating system. So you had these kinds of hoops that you sometimes had to jump through. It typically was because of constraints of the BIOS that they had these issues. So you might have multiple partitions just for a particular operating system. Now, of course, technical issues, you love them. So anyway, the master boot record doesn't really know what constraints operating systems need to satisfy. Like Linux may want to be loaded at one address, Windows may want to be loaded at a different address, some other operating system may have a completely different set of constraints. So what do? Typically the partition would again devote its first sector to be the bootloader for that operating system. Obviously, Linux swap doesn't need a bootloader. It would have a sector without 55AA at the end. But the Linux boot partition would have a bootloader that says this is what to do next. Okay, so you can see already we're starting to get layer upon layer to get this system up and off the ground. So the master boot record has to get the next bootloader going. Now, of course, you have a further constraint that this partition data takes up space as well. For partition table entries, they were 16 bytes per entry. I loved playing with these when I was younger. I would typically write assembly language programs to go in and manipulate these things in ways they were not intended to be manipulated, but it was fun. So the older style format, you can see 512 bytes minus the boot signature, 55AA, minus this partition table, leaves you 446 bytes to get the next stage loaded. That was all the space that you had. Newer master boot records contain even more information. Okay, so that shrinks it down even more, and notice now you have 434 to 436 bytes, depending on the MBR format, and it's broken into 2 parts. So now you have a chunk of code, and you have to jump to another chunk of code just to get your program running. So you know that you're going to lose some space to jumps, anytime it's broken apart like that. So that's not good. And you can already see that if you have some kind of sophisticated bootloader, there's no way that it could possibly fit into 434 bytes. So again, you may be familiar. Does anybody use Lilo ever? So that used to be a really popular loader when I was young. Stands for Linux loader. Probably everybody's heard of Grub, right? If anybody who runs Linux has probably heard of Grub. And they even have new versions of Grub now. Grand Unified Bootloader. They're hundreds and hundreds of kilobytes. There's no way that you could fit that all into a boot sector. So Grub has a Grub bootloader that loads the next stage of Grub. And then that goes ahead and does all of the sophisticated bootstrapping stuff. Same thing with Lilo. These bootloaders have multiple stages as well. So the MBR loads a partition bootloader, but it's interesting because remember the partition bootloader, what does it expect? The partition bootloader expects to be at 7C100 where the MBR bootloader is. The partition bootloader expects to see DL being the address or the disk drive number of where it should be loaded from. So we have an issue that the MBR loader needs to replace itself with the partition loader. So it emulates the bootloading mechanism using chain loading. If you've heard this term, if you haven't, basically it's just the process of getting one bootloader to load the next bootloader. So what it does is it loads the next bootloader into 7C100, where it's supposed to be, and then jumps to 7C100 and starts running it. Okay, pretty simple. Of course, the MBR loader is there right now. And so typically what these MBR loaders do is they will copy themselves to another location, frequently 600. They'll copy the sector data to 600, jump back to where it is now, and then they can go ahead and chain load the next bootloader. Why is it 600? Well, because it's available memory. Basically at this point, the computer is like this giant field with nothing in it, and you can do basically whatever you want. The only things that are really constrained are the interrupt vector table is at the beginning of memory, the video memory is at a specific location, and the other issue is you don't know how large the computer memory is unless you ask the BIOS. And so you have to ask the BIOS, how much memory do I have? And then you can use all of that. And of course, then you have other issues, which we will talk about next time, like this A20 address line. So the original PC could only access up to 1 megabyte of memory. If you want to access more, you have to turn on that address line. And that was all fun too. So, all of these issues you had to deal with. But what it means is bootloaders can kind of do whatever they want, which is kind of fun. Okay, so bootloaders are relying on BIOS to do their thing, and they basically have the same issue that we talked about with applications running on an operating system. They don't know the addresses of the BIOS operations, so they use an indirect interaction using interrupts. Now, this is not to trap into a kernel, because everything is running at the same protection level. They can just go ahead and invoke those interrupts without any problem. So int 10 being in hexadecimal. I just say int 10 because I don't like saying int 10h or int 0x10, which is, all of it does not roll off the tongue. But that is basically all the video interactions. You want to change the display mode, int 10. You want to print a character, int 10. You want to draw a pixel, int 10. It has various operations. You can specify it in AH, and then the other operation or other parameters go into the other registers, and then off you go. Okay? So this is a simple example of how to print a character in teletype mode. You don't have to study this too carefully because I give you code for printing strings to the console so that you can print basic diagnostic information to your console, because it turns out to be difficult to debug bootloaders. Thankfully, there's a way, and I will show it to you on the second assignment. So it's actually everything you write for the second assignment is pretty straightforward to debug, except that you don't have seg faults if you're in a PC booter, unless you install the appropriate exception handler on the processor and actually say, yeah, tell me if I seg fault. No, you're just going to crash. The machine's just going to crash. So it's kind of exciting to program. It is. It's really fun. And it's like you bang your head against the wall for like 9 hours, and then you get that one little bug fixed, and you're running around the house celebrating. This was me like a few days ago, running around the house celebrating, and my wife comes in to look, and all the computer screen says is hello, and that's it. And it's like, yeah! Never did I write so much code to get hello on the screen. So anyway, int 13 is for disk access, and so this is how you would read a sector from the disk. You can see that this is a simple approach. AH is 2, AL is the number of sectors to read, CX is the cylinder, and the sector number, wait, what? And then you have the head. Again, what is that? And then you have the disk drive to read, which is just, like I say here, 0 and up are the floppy drives, and 80 and up are the hard disks. I do not know how to access USB drives and so forth. I just haven't been in BIOS world long enough to know, how you access those modern devices. And you can see that the loaded sector data goes into a particular location that you specify in other registers. We'll talk about that in a moment. Now, of course, cylinder head sector. This uses the old school way of accessing disk drives, where we actually always had the same number of sectors per track. And we had cylinders that were comprised of the same track on various platters and so forth. It was really limiting. You could only access up to about an 8 gig drive. I don't know if anybody here has a drive that's 8 gigs or smaller anymore, unless it's one that you have on your keychain. Okay? And even then, you probably have one larger. So this is old, and we don't like it. And you'll notice how I even say 255 heads. It turns out that Windows had a bug all the way up to Windows 95, where if you tried to have 256 heads on a drive, the operating system would fall over. Yay, go Windows. So a few issues like that. So there were a lot of limitations with cylinder head sector addressing, and so people created a new one called logical block addressing, where basically you just have a single index, starting at 0 all the way up to the maximum sector number on the disk. And so you had extended read sector, which is AH is 42, and then you have DSSI is this disk address packet. And I say it's a simple data structure, except programming simple data structures in assembly language is not simple. But these are the various things that you specify. The number of sectors to read, the size of the packet, where to put the data when you load it, and also where to start loading. And you'll notice that these values are big because we have large drives now. So this disk address packet actually allows you to talk to a very large drive and load data off of it into memory. So that's the idea behind the disk address packet. You'll have to do something like this on the assignment. Now notice that I said DSSI is a segment offset pointer to a disk address packet. So the question is, what is this segment offset thing? I don't know if you guys, in 5X, do you still use a 188 at all? Yeah? Okay, so you guys will be like, oh man, segment offsets again. This is so annoying. Basically, this is the old school way that the Intel processors would access memory. So IA32 has probably 4 or 5 different modes that it can actually interact with memory. We're going to talk about a couple of them, and on the assignment, you'll get to use one that we don't really talk about, basically flat addressing without paging, which is really simple to use, and it gives you your full address space, so that's kind of nice. But yeah, like I say, some are advanced, and some are just there because they've always been there, and everybody expects it now, which is too bad. And the funny consequence, I always think this is hilarious, is that when you start up your completely badass, I just bought it yesterday computer, it starts out acting like an 8086. And so the bootloader, this is another thing the bootloader has to take care of, is get it into awesome hex core i7 mode as opposed to 8086 mode, where it's acting like I only have 640 kilobytes of memory and I can't use 32-bit values and I don't even know what 64-bit is or any of that stuff. You have to get it out of that mode into cool modes. Okay, so IA32 has a segmented memory model, and what this really means is that we divide memory into regions. They just happen to be named segments. Okay? And what this region is, or how regions are managed, is dictated by the memory addressing mode. And so real addressing mode is very simple. We have only 16-bit registers, which is not entirely true. I'll mention that in a second. But the instruction pointer is 16 bits. Flags is 16 bits. You have all your general purpose registers. Notice we chopped the E off of them. They're only 16 bits. And the segment registers, CS, DS, SS, and ES, and then of course you have FS and GS if you really need more. They used to not have them, but they do now. Everybody has them now. So, but I almost never need them. Typically you use DS, SS, and ES, and then obviously you always use CS. Now if you're on a 32-bit processor, you can still access the 32-bit registers in 16-bit code. But the instruction encoding is different than in 32-bit code, which is super fun. And I ran into a hideous bug when I was creating the bootloader for you guys. Thankfully, it's well documented now, so you shouldn't run into that same issue. Okay. So real addressing mode, we have 20 bits of address space, so 1 megabyte. MIB is not men in black. I suppose it could be, but it means megabyte or a mega binary byte. So it just means like the 2 to the 20 as opposed to a 1 with 6 zeros. So it's a little bit more. 20-bit address, you can see that we combine the segment value and the offset value. This is how we compute addresses in real addressing mode. So segment, shifted left 4 bits, multiply it by 16, and then we add in the offset. Okay, so that value is called a segment selector. And you notice a couple weird consequences. It blew my mind when I was trying to understand this as a kid. Okay, each segment is 64 kilobytes, and they overlap. Just really confusing. But each segment is 16 bytes further than the previous segment. Okay, which means that you can have multiple addresses that refer to the exact same byte. Okay, so these are two addresses that actually refer to the same byte, A5C0 2DE1 and A5BF 2DF1. Let the fun commence. So the segment register that you use depends on what operation you're performing. Clearly, if you're using IP to look up an instruction, it automatically, implicitly uses the code segment. If you use push, pop, push A, push F, pop whatever, then it's going to use the stack segment register. If you do anything with memory, it's going to use the data segment register. But you can also specify the segment register. Or another really clever idea is set them all to be the same segment so you don't have to care, which is what I usually do. It's like, why why deal with this stuff? So if you wanted to pull a byte of memory because you were looking at a particular instruction or copying an instruction somewhere, you could use CS as the segment selector. Or if you want to get something off the stack because you want to access an argument, then you can specify the stack segment selector, and so forth. Okay? And like I say, just because you do something with the stack pointer does not mean that it will automatically use the stack segment. So this is why it's really nice to set DS and SS to be the same, because then you don't have to worry about these things. Okay? So this is real addressing mode. You'll have to know a little bit about this because you will have to write some bootloader code, and it will be in real addressing mode. And you'll actually get to write the code that gets you into protected mode. It's not long, it's just confusing. So, it's like the 4 most confusing instructions you ever wrote in your life. Actually, one of them is really simple. The 3 most confusing instructions. Okay. Anyway, so you can move values into these things except for CS. Because if you're doing a move into CS, you might, the processor's like, no, you can't do that. You just have to jump. Okay. So bootloaders typically set up their own data and stack. Notice we just set AX to 0, move that into both DS and SS. You're not allowed to move constants into the segment selectors. You have to move a register value into the segment selectors. And you can see, again, where should the stack go? Wherever we want it. So we just start it at F000 and it'll grow down from there. That gives us plenty of space. Now, what would happen if an interrupt occurred between these last 2 instructions? Again, 5X folks all already know the answer to this. So I set the stack segment, I change the stack segment selector, and then an interrupt occurs. Well, what does the interrupt do? Yeah, it pushes a bunch of stuff onto the stack, and then it tries to jump to the interrupt handler. Well, that part will work fine, but when the interrupt handler returns, we end up in La La Land. So we really shouldn't have an interrupt between those 2 operations. And so, like I say, it would basically we'd have some horrible issues start occurring. And so when you move anything into SS, interrupts are suspended for 1 instruction. okay, sure. I don't know how they found this problem, but probably somebody thought of it and said, well, we should probably design this effectively to avoid this issue. So basically it allows us to do SS and then SP in two instructions. Now you can also use LSS if you want to set them in one, but who cares? Okay. Also, like I mentioned before, the real mode interrupt table is different than the protected mode interrupt table. When I first wrote my bootloader, I had a problem that I failed to realize that I was accidentally loading the rest of my program over the interrupt vector table. And so I was confused as to why my computer kept falling over. Well, I was overwriting the interrupt vector table and then trying to call BIOS interrupts and things were exploding. Okay? So you have to be careful because anybody can write to this memory region and it can really mess things up. Typically you won't mess with this in your bootloader, you just use it. But when you transfer into your own program, then you need to go into 32-bit mode and set up the interrupt descriptor table. Okay? So anyway, you have various things that you can control with that. Okay, we won't talk about that. Now, IA32 also has protected mode, which is really nice. You get all the memory protection facilities that IA32 has to offer, plus you also get optional paging. You can do address translation, all kinds of other cool stuff. But it is optional. The other thing is you still have these same segment registers, which is kind of weird. They're still 16 bits, but now they're used differently. Okay? So you still have CS EIP, SS ESP, DS operations for moves and so forth from memory. So these segment selectors no longer are used directly. We don't use them in some function to compute addresses from segment selectors. Instead, they use something called the global descriptor table, which describes all the memory segments that your computer is configured to have. Okay? So basically the descriptors say this is where the segment starts, this is how large it is, these are the memory protections that you're required to have for that segment. And so there's a register, GDTR, which you can load with LGDT. You'll have to do that. I give you the instruction. It's very straightforward. I give you the global descriptor table register, the global descriptor table, so you don't have to figure it out. It's complicated enough. So you just plug that descriptor table into the global descriptor table register, and then it will start being used by the processor for memory access. There's various segment descriptors. Okay? And like I was saying, the size of the segment, the privilege level of the segment, the type of the segment, is it code, is it read-only data, is it read-writable data, so forth. And so, and the base address is really important. We'll talk about that in a second as well. But what we can do is we can set up a flat addressing model where we basically say, yes, this segment starts at address 0, physical address 0, and it is the entire address space. So it's just a one-to-one mapping. And you can say, here's one that's code, here's one that's data, and so forth. And then the segment selectors, so CS, DS, ES, all of those, SS, are just indexes into this table. So CS is a specific segment descriptor index, and so forth. Okay, so yeah, this is where it starts to get dry, and I apologize, but you have to understand. So segment selector offset, segment selector is 16 bits, offset is 32 bits. That is a logical address. And it is mapped to a linear address using the segment descriptors. So notice, we pull out the segment selector's descriptor, we pull the base address, that's the reference point, we add the offset, which is from the logical address, we add the offset to the base address, and that gives us the linear address that we then access for that segment. You can see why I like to set the base address to 0, because then it's just a simple one-to-one mapping. You don't have to think, it just goes across. If the offset ends up being beyond the size of the segment, then you get a protection error. You tried to access beyond the segment. So you can actually use this to constrain memory relatively effectively. Now what happens after this? Well, then you have the virtual memory system. And that linear address will be mapped to a physical address. Now, why am I telling you all this? Well, one of the things I want you to see is that the IA32 processor is incredibly sophisticated. It has all this cool stuff that it can do, but we use like a little fraction of it because we really don't need that much for our operating systems. Frequently, we just do flat address spaces, and then we do virtual memory so that we can map blocks to physical blocks and do our whole thing. We don't really use this segmented model very much. It used to be that people loved the segmented model because they didn't really have paging. You know, there's a history there with virtual memory. We'll talk about that when we talk about virtual memory. But we don't need it, so we don't really use it. See a few other things. So pictorially, this is what we look like. Segment selector, we look up the segment descriptor using the global descriptor table register. We add in the base address and the offset to give us a linear address, and then that is mapped to the physical address by the virtual memory hardware if we turned it on, which we don't have to. Okay, any questions? Really straightforward. You don't have to think about this too much, thankfully, for your PC booter, but this is the mechanism by which it's translating addresses. This will become a little bit more important when you get into the fourth project and actually do user mode versus kernel mode. This will become an important thing again. Okay, so logical to linear. You can do very complex segmented memory models, but we basically always use a flat memory model because it's really simple. Why do all that segmentation? Well, there was a reason, but we don't do it anymore. And we use virtual memory to actually impose process isolation. Okay, so that's the deal there. You'll see this note when you get into the code. It's not a big deal to talk about it now. Does anybody have any questions? All right, so we're okay right now. Let's see, a few other things. Interrupt handling. So this is interesting. I'm going to throw this up here. There's this whole other thing of like, how do you actually dispatch interrupts when you change protection levels? Remember, when you change protection levels, you change stacks. And you need to configure this task register to set up the change of protection levels. But we don't need it for our PC booter, so I'm not even going to talk about it because it's just extra information. So what we'll do next time, you can see, oh man, all we did was talk about the state of the machine when it boots. Okay, we went through like 3 or 4 phases of bootstrapping. We're still in BIOS. We're still in real addressing mode. We still only understand 16-bit values. We can do some 32-bit stuff if we need to, but not very much. So what we'll talk about next time is the rest of the process that gets to the operating system kernel, gets into protected mode, configures stuff, and then we'll spend some time talking about UEFI because it really is the wave of the future, and it's going to supplant all this BIOS stuff. So, all right, we'll see you all on Friday. All right, so what we're going to do today is finish off our bootstrap process, and you'll see how ugly it is, and then we'll talk about the solution that people are starting to adopt. And it's pretty widely used now. At some point, I'm going to have to redo the second assignment, and I don't know, hopefully not Pintos, we'll have to see, but to start using UEFI. And I'm not excited about that, but hopefully it won't be too horrid. But we had started talking about bootstrapping and this whole issue that we have a machine that requires a program to know what to do, but it doesn't have one when it starts. And so there's a process by which we get to the point that it's actually executing our program. And so, like I say here, it's a series of increasingly complex bootloaders. Each stage takes a step forward, it loads the next stage, and then off we go. And so we start out with a very simple step of saying, hey, here's 16 bytes, do what you will with it, and typically it's jumped to something more complicated, and that loads in something more complicated, and blah, blah, blah. We go down this process. Okay, and we started covering the IA32 bootstrap process, and like I say, the details were grungy so far, but they get worse. And the real reason why is because we have to maintain backwards compatibility. Do we really? Well, yes, there's a few people who still try running DOS on their computers. You know, they're fancy advanced systems. I might have tried it once or twice. So, you know, you still have to maintain backward compatibility so these old pieces of software don't get confused. They know what to do. So IA32 has segmented memory. That is the general approach of the IA32 processor instruction set architecture. We're going to talk about that a lot more when we get into virtual memory. So just for now, why? Well, it's just the way it's designed, and we'll talk about more of the reasons when we get there. And there's multiple addressing modes. We start off in real addressing mode. Remember, we have a segment value and an offset value, and the segment, it's called a segment selector, but it's a 16-bit value, and it's actually used to compute the address. So we shift it left by 4 bits, or we multiply it by 16, and then we add in the offset, and that gives us our address that actually goes to memory. So that gives us our physical address. Protected mode is much cooler, and it's much more configurable, and so we have this thing called the global descriptor table, which we can use to specify the details of each segment. Where does it start in physical memory? How large is it in physical memory? What are the protections for it? And so all of these things are used to translate addresses in this way. So you take the segment selector, look up in the global descriptor table. Okay, what's its segment descriptor? You pull out the base address, you add the offset to it, and that gives you a linear address. So that's good. That's part of the process. What we do then, so just to touch on what operating systems generally do with this model, you can do a lot with it, but OSs generally just set it up to be simple. The base address is 0, the size is the entire address space, and so this mapping is basically just a one-to-one mapping. The offset or effective address just gets translated straight down, add 0 to it, who cares, we come to a linear address. So this mapping part is simple, okay? But there's a giant part of it that I'm leaving out right now because we're not talking about virtual memory. That little map to physical address thing in the bottom right corner is the virtual memory system. So this is where the page table, page directory, base register, all of that stuff fits in there, and we use that to map the linear address to a physical address. Okay. But what's really cool is we can just turn that part off too. So if we want to do that, then the linear address is our physical address. We don't do any mapping. But most operating systems, they don't use the global descriptor table to do their process isolation, although they could. Instead, they use the virtual memory system to do their process isolation. Okay, so that's just the overview of this stuff. Okay, so we talked about starting up at address, lots of F's and then a 0. And we do the power on self-test. We talked about all of this stuff. The only interesting details are the boot sector is loaded by BIOS into a specific address, 7C100. And we have 512 bytes to do our thing. Really, we only have 510 bytes. But really, we only have like 430 bytes if we're a real operating system. So, and if it's a master boot record, then we need to go ahead and chain load the next boot sector that's selected. Okay? And so that we sort of fake this process for whoever comes next, if we need to chain load. Okay? So finally we get to a bootloader that's the operating system's bootloader, and that's the thing that gets to start setting up for the operating system. So that's what we're going to talk about today. Okay? It loads the OS kernel somewhere into memory, and then it jumps to the kernel bootstrap code, and that startup code sets up the hardware so that the operating system kernel can actually do its thing. Part of this is to transition into protected mode, which is exciting and scary at the same time, because in one way you are opening up all the facilities that the hardware has to offer, but on the other hand, you no longer have BIOS to take care of things for you. Now you have to start doing things yourself. Okay? There are other annoyances that you run into on IA32 or x86 systems. So the first thing I mentioned briefly before is that you have a 1 megabyte, or technically it's a 1 megabyte, but I hate saying that because it sounds silly. It sounds like you're making up words. But you have 1 binary megabyte of address space. So you have, 20 address lines, A0 through A19. But if you look at real addressing mode, you realize, hey, I actually could access past that 1 megabyte address range. Okay, so for example, if you do this FFFF, then you can end up going a little bit under 64K past that 1 megabyte barrier. Okay, so if you have a system with 4 megabytes, then that's actually some space that you'd like to be able to utilize. So you start wanting to expand your address space. But the original 86 had only 20 address lines, like I was saying, A0 through A19. So anything beyond that, if you think about what would happen if you tried to execute past the end of this, you would just wrap around. And unfortunately, there were programs that relied on this, typically BIOSes that were in that space. And so they start executing, they fall off the end of the address space, but thankfully the world is round, so they end up on the other side, coming around the other way. Why would a program ever do this? I don't know. Does anybody do this now? I sure hope not. They should be beaten if they do. But so BIOS needs to support this. We need to be backward compatible, so we disable the A20 address line if there is one. So that we can retain only that 1 megabyte address space and this really bizarre behavior that some weird, stupid programs actually depended on. So A20 address line is disabled. It's forced to 0 at startup. If I want to access more memory than 1 megabyte, then I have to re-enable that 820 address line. Yes, every operating system has to think about this. If you're like, seriously, you can't be serious. Every operating system has to think about this kind of thing. Okay, so yeah, like I was saying, for backward compatibility, the 820 address line is typically left disabled at startup time, and so it has to be re-enabled. Sometimes it's taken care of by BIOSes, because a lot of people say now, wow, that's a really dumb constraint, and so the BIOS will take care of it. Bootloaders like Grub take care of it for you. So Grub, for example, sets up the hardware in a specific way so that operating systems can just know that it's all good. So thank you, Grub, except now you've actually made operating systems a little bit more complicated, because now they have to check if it's disabled and then re-enable it if it's disabled. But if it's already been enabled, then they shouldn't do anything. And so that's another thing they have to think of. Instead of just always re-enabling it, now they have to check as well. So whatever. Thank you, Grub. That kind of sort of made life a little bit different. Okay. So the other step. Startup code has to configure protected mode and then switch into it. And like I said, you also have to enable virtual memory. Most operating systems use virtual memory, so that's something else that you have to set up. Like I said, you have to at least set up 2 segment descriptors, one for code and one for data. Because remember, there's CS and there's DS, and the processor automatically uses various segments when it does things. So you have to make sure that you have a code segment for the code so that when it loads instructions, it always automatically uses the code segment. You have to have a data segment so that MOOVs will automatically do the right thing. Obviously, if you'd like to use a stack, then you should set up the stack segment as well. Okay? And if you're doing virtual memory, then you need to set up a page table as well. I'm not going to spend very much time talking about this. There's some really interesting and clever things you have to do in your startup code, because typically one of the things that happens is the kernel is loaded below 1 megabyte, but then you need to move it above 1 megabyte. In fact, you move it above 3 gigs if you're on a 32-bit address space. Well, how do you do that? Well, you just configure the virtual page table mapping so that the kernel appears in 2 places. And then the low part jumps to the high part, and then voila, you're where you're supposed to be. So the kernel has to think about these things. Thankfully, we don't have to talk about it right now. Okay, so we switched from real mode to protected mode. And again, more complicated than you think. The work you guys have to do on the second project is like the simplest possible version of it. Okay, so there's a few details even omitted from what I'm going to give you, and it's like an 8-step process here. So you disable interrupts, and the IA32 manual is really explicit about this. They say if any interrupt occurs at all in this process, the world will end as far as the processor is concerned. It's like, you know, all hell breaks loose. They even say if it's possible to disable non-maskable interrupts in hardware, disable non-maskable interrupts. That's how serious the manual is about. You've got to disable interrupts. Next thing you do, you set up your global descriptor table, because remember, this is how protected mode figures out where addresses should go in physical memory. So we have to set up that mapping. And again, it's really straightforward. The booter that I give you, the global descriptor table is stuffed into the boot sector. That's not normally how you would do it, but it's small enough. It's like 16 bytes or 24 bytes. Just cram it in there and just point to it with the global descriptor table register, and that's all you have to do. Third thing, and this is something we don't do in our booter, but operating systems have to do this because remember, they have multiple protection levels that they run code in. Our booter is all in ring 3 or ring 0, so it's like we can do anything we want, which is probably dumb, but it's the way we do it. Operating systems start out in ring 0, but then they also want to run code in ring 3, and when you transition between the two, you switch stacks. The task register says how to switch stacks. That's why we don't have to do it, because we never switch stacks. But if you're going to have user space and kernel space, then and user mode and kernel mode used in your operating system, you have to have the task register set up. Finally, you get to turn on protected mode. Yay! That's it, right? No, there's more steps after that. But you'll notice that you write to control register CR0. It's full of bits that enable and disable various things. One thing that's kind of interesting, I'll just mention this as an aside. I don't know if any of you are going to try to use floating point in your booter. If you do, be forewarned, there may be icebergs that you run into because, well, there is a coprocessor on all of our modern IA32 processors, so that's not a problem. And we're not doing context switching, so you don't have to worry about saving floating point registers and so forth. So I think you'll probably be okay. It should be fun. See what happens. So if you try that and you have success, let me know. I might even give you a couple of bonus points for that, because that would be a cool thing to know. Anyway, there's some details in CR0 you can configure as far as coprocessors are concerned. Okay, and of course, if you turn on paging, then you also need to set CR3, which is the page table base register, or the page directory base register, so that you can actually have a page table. Okay, so we're all done, right? Well, the only issue is the processor is still running in a 16-bit real mode code segment, because that's cached inside the processor. So even though it's in protected mode, it's still using all that real addressing stuff. So we need to change the code segment to the new code segment we just set up in the global descriptor table. The way that we do that is by doing a long jump, because a long jump specifies the segment selector as well as the offset to jump to. Okay? So what do? Well, we just say, use this code segment now. Where do we jump to? The very next instruction. Okay? Simple enough. You'll see exactly how to do that in the booter, because this is part you do not have to do. Okay? It's mechanical, so why make you guys do it? Okay? So anyway, you do a long jump to the next instruction that forces CS to be reloaded, and obviously you go from using IP to EIP, because now you're in 32 bits, and off you go. So you're pretty close now. Next thing you have to do is set up your other segment registers, which again I think I do for you. I can't remember, but you have this data segment you set up. So you set DS and SS and ES and FS and GS if you want to use those. You point them all to the data segment selector you set up. And now you're basically all set. If you want to handle interrupts, which again all operating systems do because polling is dumb, then you set up the interrupt descriptor table register. And it turns out that you could actually build all of the facilities you have to build in the PC booter without interrupts. You could pull the keyboard until key data shows up. It's really dumb, because you'd like to actually be doing other things. And you could build a timer by figuring out how fast the processor goes and creating a loop of the appropriate size so that you actually just spin on the processor until a certain amount of time elapses. That sounds great. So we don't have to use interrupts, but really we should. So we set up the interrupt descriptor table register with a new interrupt descriptor table. Remember, previously it was an interrupt vector table, which is useless in protected mode. Re-enable interrupts, and off we go. Okay. Now we can actually start doing kernel-y stuff. Okay, any questions about this process? Yes? Which register does it use to determine the base address? So if you're talking about a segment, the base address will be in the segment descriptor that's in the global descriptor table register. What's used to index into that is the value of the segment selector. So for example, CS will be set to some value. And what you'll notice in our operating system is it'll either be, I think either 1 or 3, because those are the indexes into the global descriptor table. You'll actually have 2. One is for user mode and one is for kernel mode. And in that segment selector, the segment selector, I can't remember if it's 8 bytes, it's probably 16 bytes or something like that. But one of the fields in that 16 bytes is, here is the base address, or here's the value to add to whatever addresses the program emits. The CS is the index into that table. Yeah, well, the program can change CS, but if it changes it to something that's not in the global descriptor table, then the processor will generate faults, and the operating system will step in and... Yeah, so if it tries to change it to the kernel one, it's allowed to, but what will happen is when it tries to touch that memory, it's still in user mode, and the kernel memory is set up that it's only accessible from kernel mode, and so when it tries to access it, you'll generate a protection fault, and the OS will step in and kill the program. So yeah, it's interesting because you might say, well, the program is still allowed to set it to these other values, but the system is set up so that there's always protections enforced so that if the program tries to do something naughty, it will still generate faults. The operating system will still find out the program's trying to be naughty, and the kernel can kill the program. So you're always protected that way. Does it make sense, everybody? It's kind of really important to understand it, because we'll start getting into user mode in a couple of weeks, and you'll start seeing how this all fits together. Okay, any other questions? Yes, exactly right. We do have to change into user mode at some point. We're not going to talk about that today, but that is another thing that happens. If you think about it, the kernel, what I'm going to talk about next is the kernel still has to do some other setup stuff. Not very much, but it has to do some other setup stuff. And then typically what it does is it creates the first process. And the first process is in user mode, and it tends to be an idle process, so that if the processor has nothing else to do, it can always go back to the idle process, and that runs in user mode. And so that's how it gets into user mode. So yes, at some point the kernel has to transition into user mode. And that's when you exit the kernel for the very first time. But all this other stuff still happens in kernel mode. Okay, any other questions? These are cool. They're just a little bit ahead of our focus right now. But they're still cool, important questions. Right? All right. Let's see. So yeah, the kernel is ready to take over. Now, of course, we can't use BIOS anymore, which is lame. So what do we do now? Well, this is where we have to start thinking about device drivers. And what you all will be doing on the second project is creating really simple, limited device drivers that have to support one device apiece so that they can interact with the computer hardware. So you want to have some encapsulation around this grossness, because all hardware is gross in some way or another. I suppose there's beautiful hardware to interact with, but a lot of it has little grungy details and nuances that you don't necessarily expect at first. And so you have a device driver that encapsulates that grossness and exposes a very simple, clean interface. Like Linux has character devices and block devices. And block devices encapsulate all the details of actually interacting with the ATA controller that's on the bus, so that it can actually send and receive data to the disk controller. Those kinds of things. You don't want to do that in your program. You just say, here's a block of data, do stuff with it. Okay, so that's what the device driver does. And so frequently what happens is the devices have already been initialized to a certain point, but they may not be the way the OS wants them to be. And so it can go in, reprobe devices, reconfigure them so that they're the way the OS wants them, and then the device driver can just carry on doing its tasks. So typically you'll see hardware reinitialized at that point. Okay, so that's the general idea. This is what gets us up to the kernel beginning to do kernel-y stuff. Scheduling, virtual memory management, process, address space isolation, all of that kind of stuff. Okay, so these were the details. I just want to throw these up here so you can see the whole mechanism. But you can see how each step has to take a little step forward to expand the capabilities, expand the complexity of what we're able to do, and get us to the next phase. So you can think of these as little steps that get bigger and bigger as we finally get into our operating system. Okay. The other thing that's really interesting to mention is that Windows also has tried to maintain backward compatibility. This is something, if you think about it, Linux has not really tried very hard to do. And, you know, it's a great approach. It certainly means that all your software is going to not suck. But like GCC will not even emit 16-bit real mode code. Like, why? Why should I when I have 32-bit protected mode to use? And that's partly why our PC booter is going to get into protected mode so that we can write the rest of our program in C instead of having to write it in assembly language. Which you may find it funny, but this may be the first time where C was the high-level language in the project you were working on. Normally it'd be like, oh, I'd really love to write this in Python, or I'd really love to write this in Haskell because they have all these really awesome language facilities. I don't have to worry about memory management and all that kind of stuff. But when your low level is assembly language, you can't wait to get into C because it's like, oh, C is so much easier than assembly language for writing code. So anyway, Windows still has to maintain backward compatibility, and so you still have DOS programs that use BIOS calls. Well, what do? It turns out to be pretty straightforward. We just replace the interrupt handlers with our own interrupt handlers that do the things that we need to do. Okay? And so this is what Windows does when it needs to run 16-bit programs that still make BIOS calls. Okay? So that's kind of neat. There's also a special virtual 8086 mode that processors, the IA32 processors have. And if you have a 16-bit DOS program, you can run it in that virtual 8086 mode so that it still looks like a real addressing mode system inside of the 32-bit protected mode. So not Windows, but IA32 has all these facilities for backward compatibility as well, and Windows leverages those things to enforce all of its operating system guarantees pretty effectively. So that's kind of a clever little technique that they use. Linux doesn't really do anything like this because why? Just run it in an emulator if you really want to run some 16-bit program on Linux. Okay? So that's another interesting little detail here. Okay, so we see that IA32 Bootstrap is hideous. There's not really any other way to describe it. So we have all of this because we want to maintain backward compatibility, even this A20 address line thing, which is just bizarre if you think about it. And of course, once we get into protected mode, we don't have any support for our devices. So we have some issues that we have to deal with. And I've kind of harped on A20. Well, there's a reason. It's even worse than you thought. You have 3 different ways that it can be enabled. And if you think about it, that means you have multiple ways to check if it's already been enabled. So you have an interaction with not any addressing subsystem, but the keyboard controller. Because when they were designing the first PCs, they needed something to run A20 through so that they can enable it and disable it. And, oh, hey, look, the keyboard controller has a spare input and a spare output. Let's use that. So that's why you talk to the keyboard controller when you want to access more memory on these old systems. Seriously. So BIOSes started adding calls to support A20 address line enabling. And of course, the bootloader or the BIOS itself may have already enabled A20. So you have these various things that you have to think about if you want to do that. And of course, that's just A20. All these other hardware facilities have a whole bunch of other little vagaries. Like one of the things I want you to do on the booter is to do some basic interactions with VGA. Okay, well, that's cool. Has anybody here done basic VGA? I know this is really basic compared to what you can access now with DirectX and OpenGL and all that kind of stuff. Anybody tinkered with VGA before? So that's all we had when I was in high school, and that's what we had to program. And so I wrote programs that would talk directly to the VGA card, writing to ports and switch it into different graphics modes, switch it into freakish graphics modes, change the color palette, which is something you could do. When you had programs that would fade in and fade out, that was mind-blowing at the time. And the way they would do it is they would put all the data into the video buffer, and then they just changed the color palette. So it would change the mapping from the pixel value to the colors that were sent to the graphics monitor. And so you could manipulate all of that through I/O ports. The only problem is there were standard ports, and then there were special ports for whatever specific VGA hardware you had. So all of those kinds of things also factor into providing device drivers. And that's why you have a device driver for this card, and a device driver for that card, and a device driver for this thing and that thing and the other thing. You have to support all the different ways that people approach things. Standards are really only suggestions a lot of the time, which is too bad. Okay, so people tried to start resolving this issue by introducing new mechanisms available in the system. So we had plug and play, which you may have heard of before. Basically, that was a way of having devices talk to the operating system and tell them, this is the kind of device I am. These are my capabilities. These are my address ranges I would like, and so forth. And so the hardware bus had to actually support it. You didn't see it in the older, there was a bus called ISA, which just stood for Industry Standard Architecture. It was okay, well, that's nice. It's the industry standard. Let's use it. But then there was another one called PCI, Peripheral Component Interconnect, which came along, and the devices on the bus could actually say, hey, this is what I am. So the standard actually was changed to support discoverability. And we still use it's we're 4 or 5 versions down on PCI now, so it's very advanced now. It used to be only a 33 megahertz bus. It used to be really slow. I think you could access 16 bits at a time, or maybe 32. Maybe they had taken the first step in the 32-bit, and so that was very exciting. But anyway, so you have all these different buses, and USB is a really good example of a plug-and-play bus as well, where devices are discoverable. If you're curious about playing with this stuff, and you do want to stay within the comforting world of Python, you could look at PyUSB, which actually allows you to query the USB devices that are connected to your system. And you can look at their device IDs. Those are all standardized. You can ask them other questions about what they can do. So it's kind of fun if you want to tinker with that kind of stuff. But all these buses were designed to facilitate discovery of devices on them, so you could find out what they are and how to interact with them. So once you start having plug and play, then the BIOS starts getting more sophisticated in what it provides to the operating system. And so typically you would see BIOS build tables of data that the OS can then look at. And we started in '97 with this thing called the Intel Multiprocessor Specification, which I don't know why, but just for kicks, I threw it into the specs directory so you can look at it. It's kind of fun to read how to actually discover multiple cores or multiple processors on your system. And it builds tables that you could then go in and pull all the details of your processors. And notice important details like what are their APIC IDs. Because if I'm going to send a message to another processor, I have to be able to send an inter-processor interrupt. So you have to know its APIC ID. So you have to get that somewhere. Okay. Multiprocessor spec also specifies multiprocessor bootstrap, which is basically like single processor bootstrap, except that all the other processors instantly run a halt instruction, so they all stop, and then the one booting processor has to set up so that they can start running, and then it sends an interrupt to them all to wake them up, and then they start doing their thing. So you can read about it in the multiprocessor spec if you're curious. Okay, so ACP is another very widely used standard, Advanced Configuration and Power Interface. And again, it basically has a whole bunch of tables that say, this is what the hardware has. This is what we can do with the hardware. And all of it was accessible through this one entry point. Well, what is the entry point? Well, it's a structure. And the structure starts with a signature. Let me see if I actually say this here. No, I don't. I think I say it on the next slide. So you have to hunt for this root system descriptor pointer because you don't know where the BIOS might stick it. So you have to find it, and then you can start utilizing it. And like I say, the tables include all the details you might need to know about all the major parts of the system. Set up by the firmware, and then the operating system can access it. And this is all based on pluggable devices that are discoverable on buses that support discovery. Okay, so we have to search for it. It could be in the extended BIOS data area. Let's look there. Or it could be somewhere else. Let's look somewhere else. And so you have to kind of hunt for it. And so this is like operating systems that supported ACP had to go through this process. They had to look for the signature RSD space, PTR space, and then there was other stuff, and then there's a checksum. And what you would have to do is hunt for that sequence, and because I suppose it's possible this signature could occur in some other context, it's hard to imagine, but you had to compute a checksum, and if the checksum computed properly, if I remember correctly, you just add each byte together and see if the final result is 0. If you add them all together, so you have overflows occurring and so forth, but if you end up with a checksum of 0, then you're happy. You know you've found the root system descriptor pointer, and then from that, you could follow pointers to all the other tables. Okay, that sounds good, but what if the root system descriptor pointer table doesn't have an entry for something? Well, then you get there and the checksum doesn't add up. So you have to keep computing checksums as you navigate this table. Okay? So it's a little bit frustrating, but I suppose it's way better than having to talk to all these devices yourself. Okay, so this was a big step forward, but it kind of doesn't feel like it. It kind of feels like just a little step forward. All right? This was one thing I was thinking. If you aren't interested in building a game, you could always build a program for your booter that actually goes and finds these things and displays them and allows you to navigate through all of these tables of data. Probably way more boring than it even sounds. So, but it would be another thing that you could consider doing. All right, any questions on ACP? All right, so you can imagine that operating systems could use this information very well. Now, thankfully, we don't do that anymore, but still the hardware supports it just in case you're running an operating system that needs it. But what we've started doing is moving to a new mechanism called UEFI. Because the BIOS only helps us a little bit and only in real mode. It doesn't really help operating system. So let's get something better. Okay? And so this new standard has emerged. I say recently, it's actually starting to become increasingly distant in the past. So probably in the next few years, I'll take out the recently. But it's becoming more and more widely supported. In fact, I think most hardware now can support UEFI operating systems, and most operating systems can run on top of UEFI. And it basically completely supplants BIOS. BIOS goes away. Why did we need UEFI? Well, there was this processor called the Itanium. Anybody heard of Itanium? A couple of you. Does anybody know what's special about it? No? Sorry, it was I saw. Do I say? Well, yeah, so 64-bit, couldn't run BIOS. But what's special about it? There was something really unusual about it. It was kind of a big step for Intel, and it was a big giant flop. Yay, big risky steps sometimes end up in flops. So it was one of these very large instruction word processors. So you could have instructions that had multiple branches in the same instruction in case you wanted to do branching flow control really efficiently. It was a pretty clever processor, but it turned out to be really difficult to write a compiler for it. And so people were like, okay, this is kind of lame. I'll just get more of these cheaper processors and run them in a big cluster, and we don't really need Itanium. And of course, you know, you have 64-bit on IA32 now, or I should say x86 64, so you don't really need Itanium so much as well. One of the cool things about Itanium is it is a true 64-bit processor, whereas on the Intel IA32 processor family, we really only have 48 bits of address space. This actually had a true 64 bits of address space, so that was one nice thing. But yeah, Itanium couldn't run BIOS, but we still needed to support an operating system. So Intel started thinking of how are we actually going to do this? And so they created a standard called EFI, which then became widely supported and became UEFI. Okay? Unified Extensible Firmware Interface. Now there's actually standards for it. And like I say, it is a firmware interface standard. So we have at the lowest level hardware, as always. And then we have software running in read-only memory called firmware on top of it. And then UEFI says these are the operations that need to be provided, and these are how to provide these operations. And then other things sit on top of UEFI. Okay, so that's where it sits. It doesn't sit necessarily directly on computer hardware. It sits on top of firmware that implements the facilities that UEFI needs to provide. Yeah, you'll see why when we start going into UEFI. Okay, any questions? Alrighty. So, yeah, it is modular, which is really neat. UEFI has the ability to install custom pieces of software, and you can remove them as well. But there's a certain set of facilities that are always there so that you can actually rely on it. So you can think of this as being like a mini operating system for the computer. It doesn't allow you to run user applications. It allows you to manage operating systems. So in a sense, it's kind of like a hypervisor, but not quite, because it's really for running one operating system, not a bunch at the same time. So yeah, you can install bootloaders for operating systems. So this is what operating systems that support UEFI will do. They'll install their bootloader into the EFI system so that it can then boot the operating system. It also allows UEFI to take care of multi-boot. So now you don't have to do some weird thing with chaining bootloaders and so forth. All of them go into the UEFI system, and then it can just start whatever operating system you want. Okay, so like I said, you can install UEFI applications. Allow various things to be managed. So now we don't need our BIOS setup anymore. Now we can actually have an application installed by the hardware vendor that knows how to manage all of the settings on the computer. So it's kind of neat. You can actually do all of these things through UEFI now. Yeah, and so like it says here, you run in the pre-boot environment, so before the operating system is loaded. That's called the pre-boot environment in the UEFI documentation. And there's various tools that you can use. There's even a command shell. Okay? Has anybody experimented with UEFI stuff? Probably. Is there anything you guys haven't tried? Yeah, probably. What have you done with it? Like, yeah, oh, I know. You know, I actually tried to set up the 32-bit Linux Mint on UEFI virtual machine. And so I got into VirtualBox, and I was trying to I'm like, click the UEFI button. This should be fine. And I start it up, and it's like, here's a shell. Here's a shell in your pre-boot environment. Have fun. And I'm like, screw this, reset. We'll go back to BIOS for now. So you can see that VirtualBox's UEFI support is not really that complete yet, but it's getting there. But anyway, you can provide various kinds of applications that run under UEFI. It provides abstractions for interacting with hardware, which is really nice. So now your OS loaders can expect to talk to whatever storage device you have. Is it SATA? Is it whatever, kind of, device that you might have? UEFI obscures that. You just have simple abstractions that you utilize to load your operating system off the storage device. Or off a network, which is another thing you can do through UEFI. Okay, yeah, so there's a lot of services. I call them UEFI protocols. Well, it's not me. It's actually the standard calls them protocols. And the way to think of these UEFI protocols is in the same way as programming language interfaces. It's a set of operations that you can perform that are standardized, and protocols are the specifications of those interfaces. And so if something implements a particular protocol, you know it has a certain set of operations you can call through. Okay? And so like I say, you're loading images. So I want to pull an image off a disk and display it on the screen. Well, there's protocols for that. I want to do networking. There's protocols for that. So I can say, hey, tell me what network interface controllers there are so that I can start interacting with the internet or something in your pre-boot environment. I want to suck down an image and then decompress it into memory. Well, those are all things that are provided by UEFI protocols. Okay, so there's a ton of support for all kinds of interesting things in the pre-boot environment. Sounds way cooler than BIOS, right? I mean, already I look at this and I'm like, wow, you could build some really neat software for bootstrapping, which, I don't know, I guess it's good that I'm teaching the OS class because that's the kind of thing that turns me on. So, doesn't turn everybody on. So, let's see. So services divided into boot services and runtime services. So boot services are only available before the operating system starts. When the OS starts, the boot services go away. They're taken out of memory. Runtime services are always available. They might be things like suspend the system. I need to go into a power save mode, or I need to hibernate. So now UEFI is actually providing some real facilities to the OS to use. So the OS doesn't have to provide that anymore. Okay? So you have these two different kinds of services, and they have their own protocol specification. So you can write your own runtime services and plug them into operating systems if you wish. So it's a very extensible, I guess that's right in the name. It's a very extensible approach. It's really powerful, and I love it. I think it's a really great idea. Now, UEFI, like it says here, includes several earlier standards, so all your ACP tables are still available. They're slightly different. We'll talk about how they're slightly different in a second. Also, UEFI is kind of like Java in that it says this is the way things must be in the hardware if you're going to run. And I say it's similar to Java in that Java says how large an int is. Java says how large a char is, and so forth. UEFI says things have to be such and such a way at startup so that the operating system no longer has to jump through all these hoops. UEFI takes care of it, and the OS can just go on to doing OS-y things. Okay, so UEFI has tables in memory, and you might think, oh, okay, that kind of sounds like, rerun of the past. And it kind of is in some ways, but the neat thing about it is it actually stores function pointers in its tables as well as data. This is how the protocols are specified. We all went through in CS124 how classes expose their member functions, and same thing with interfaces. Well, if you just have a table of function pointers, then you can have them point to the implementations of your functions, and you can have a single protocol that can be implemented in many ways so that you can provide varying operations depending on device or protocol or whatever. So this is a really simple hello world. This will become project 2 in a few years, I'm sure. Okay, so EFI main, this is the entry point to your EFI application, and you get an image handle and a system table, which you have to initialize from the image handle. That's the initialize lib line. And so once it's initialized, all the function pointers have been filled in, all the table pointers have been filled in. One of them is console output. That's what conout is. And then basically you call conout's output string function to output the string hello world. And you'll notice it's a char 16 star because UEFI only does Unicode. I like computers that are usable, or I should say even in Bootstrap, they're able to use languages other than US English. Okay? So that people elsewhere in the world, there's other places in the world, it turns out, and they'd like to use computers too. So we'd like to be able to have their own languages for their Bootstrap. And so you can do all of that stuff very easily in UEFI. Okay? We still have rn, \r/n. Again, I don't know if anybody has gotten to this point in the assignment, but when you're on the PC hardware, \r I think just moves down a line, and then \n, or maybe I got it backwards. You'll have to look. No, \r is a carriage return, right? So that goes to the beginning of the line, but doesn't go to the next line, and then \n goes to the new line. So if you want to actually go to the next line, you have to do both of them. If you just want to go to the beginning of the same line, I think it's the \r, but you'd have to check that yourself.
For what it's worth, usually it's /r/n, not /n.
Yes, and so this is the way that it's in the UEFI example, if you look in the UEFI specifications, but I don't know why. You'd have to talk to somebody else. There's actually a really stupid anachronistic reason why we have 2 characters for this anyway. Does anybody know? I'm sorry? Yeah, teletype is the right answer, yeah. Because sending 1 character wasn't slow enough for the teletype to return to the next line. And so they said, well, sending 2 characters is slow enough to get the teletype to go to the next line, so we'll require 2 characters to go to the next line. I tell you, hardware is just, it is a cruel mistress. So, yeah, this is why we like drivers, because it encapsulates all of that detail. Okay, so another picture. Let's just try to get through the last few things in the last few minutes. Here's another picture of UEFI. You will notice that there's something new here. There's a couple of new things, but there's something new here, which is a can, which usually represents a disk. So you'll notice that disks are actually a very important aspect of UEFI. And this is where when you install UEFI applications, you install UEFI services, if they're not part of what comes prepackaged, then they go onto the EFI system partition. Again, probably many of you have actually seen some kind of EFI system partition, and this is part of the UEFI specification. Okay? And it tends to be something that is simple to support in firmware. So FAT32 is really popular for the EFI system partition because it's really easy to write code to do FAT32. Well, really easy compared to like NTFS or HPFS or something like that. Okay, I don't want to write it, but I mean, one could. Okay, another issue, disk sector addressing. So we had cylinder head sector, which I mentioned briefly. The real constraint here was that we could only access disks up to about 8 gigs with cylinder head sector. And so logical block addressing was introduced that allows us to get up to about 128 petabytes. Okay, if you think this is like unbelievably large, because just wait, it gets even more exciting. So yeah, we can get up to 128 petabytes this way. So that's neat, but the problem was that master boot records still only had 32-bit values for the logical block addressing. So you're still limited to about 2 terabytes, and you may have encountered this, that there's a 2 terabyte limit in some older, I mean, this is a really good reason to switch to GUID partition tables instead of master boot records for your disks, because there's no 2 terabyte size limit. And this is starting to become really serious, because I can go buy a box of, like, what, 6 terabyte disks now and just slap them into a computer, and now I have, like, a huge thing, and I'll start running into this size limit if I use a master boot record. So the solution was GUID partition tables. What's a GUID? Okay, another term that you're going to run into all the time if you haven't already. It's a globally unique ID. It's actually generated from both the current time and ideally your NIC's MAC address, so that it's actually kind of unique in both time and space. That was the idea behind it. So it's a 128-bit identifier that may actually be unique in the whole world. So that's kind of neat. And so the partition descriptors use 64-bit LBA values, which now gives us, anybody know what a zettabyte is?
A lot.
Yeah, a lot is a good answer. A billion terabytes is also a good answer. A billion terabytes, you know. Good, because I'm almost out of space, so it's a good thing that I can do that.
But it's also true that like people have petabyte data sets.
People do have petabyte data sets, but they typically don't have them on a single disk.
We're getting
Yeah, no, we are getting there, no question. But the problem is that I/O performance is still a thing. And so if I have a petabyte database, I probably want it in a bunch of disks I can access concurrently instead of one disk. But yeah, like you say, we're getting there. I'm sure in my lifetime, we'll be like, yeah, can you guys remember the day when we only had zettabytes of space? Because it's like, man, that was so small. And I'll be like, yeah, kids, when I was young, I wrote a program and it was 200 bytes and I was happy. Yeah, right.
It's funny because like playing a bunch of video games, it's really satisfying whenever something comes in and it's like 100 megabytes. And you're like,
Yes.
whoa,
Yeah.
100 megabytes.
Yeah, it's funny how these size things change. All right, let's wrap up really quick. So partition types are GUIDs now, so they're standardized. That's really nice because the MBRs had 1 byte for the partition type. Linux swap would be one value, Linux boot would be another, and they've definitely been reused over the years. So GUIDs are good for partition types. There's a few other details here which I would have loved to cover, but we're out of time, and I don't want to take up your lunchtime. But the one thing I might mention is that GUID partition tables, they put one at each end of the disk. What a good idea. Because it used to be that one sector failing, and I've had this happen right before class, one sector fails and it's the wrong sector and your disk is now useless. So having 2 GUID partition tables, one at each end of the disk, is actually a really good idea. Okay, let's see. A few other details here. We're not going to... Oh, I do want to mention, not everybody supports UEFI in the same way. Apple still sucks in this regard. It does not use the EFI system partition except for firmware updates and other staged installations that require rebooting. So if you want to install EFI Linux on your computer, it's like, good luck. You'll probably jack up your Mac stuff.
Well, that's what Refind is for.
Yes.
It's exactly designed to fuck with Mac in the way that
Yes. And so I just wanted to throw these things up here because Refind is actually on there. There's a variety of resources if you want to learn more about UEFI. Please don't turn any UEFI booter. I'll be confused about how to run it. I'll probably be able to just break into Mike's office and use one of his computers. But yeah, there's a lot of information on the internet about UEFI, so you can certainly look at that if you want. Okay, so next time we'll go ahead and start up with processes. We'll start talking about what K-threads are and so forth and how we utilize them. That's next Wednesday because we have no class on Monday, right? Yay, okay, so we'll see you all then.